Section 4.2 notes systems of linear equations in three variables. So we're going to build on what we learned in 4.1, dealing with systems that only have two variables, x and y. And now we're going to look at systems that have equations with three variables, x, y, and z. Not only are they going to have three variables, but they're going to have three equations. So these are much trickier, much more difficult to deal with. Now if you remember from 4.1, when we had a solution in a system of linear equations with two variables, we're really looking where graphically where those two lines crossed each other, but our solutions were an x-y combination, so they were an ordered pair. And graphically that would just be a point on those two lines where they crossed. Since we now have three variables in this section, x, y, and z, we don't have ordered pairs as solutions, we have what are called ordered triples. So they're still written in almost the same form, an x-coordinate, then a y-coordinate, but now we're going to have a third number, which will be a z-coordinate. So if we're given a system, or given an equation, any basic equation, but that has three variables, x, y, and z, so 2x plus 3y minus z equals 4, that would be an equation in three variables. It's not a system because it's only one equation, but we can come up with a solution, a particular ordered triple, and check and see if that is indeed a solution. So I'm telling you here that the ordered triple 0, 1, negative 1 is a solution to this equation that's in three variables, and we can verify that by plugging in 0 for our x-coordinate, 1 for our y-coordinate, and negative 1 for our z-coordinate, and check and see if we get a true statement. So 2x will be 2 times 0, plus 3y is 3 times 1, minus z is minus, the z-coordinate was negative 1. And if that equals 4, then it is indeed a solution. So we have 2 times 0 is 0, 3 times 1 is 3, and minus a negative 1 actually gives us plus 1. And at this point we can see that we are going to get the same value on both sides of this equation. 4 equals 4, that checks out. It is a true statement. So because it's a true statement, just like in any of our systems or in any equation, that is a solution. That order triple we say is a solution. Okay? So just checking if something's a solution, of course, is always easier than actually finding the solution on your own. And we're going to look at that now. Before we get in the algebraic method that we use to find these solutions, I want to talk about graphically, when we solve a three variable system, what this will look like. So there's four possible outcomes when we do this. Let's relate this back to a system in two equations, or a system in two variables. When we had the systems in two variables, x and y, we were dealing with lines, because two variables produce a line. We had three possible outcomes. Outcome 1, the lines crossed at one point. We might have a line like that, a line like that. Where the two lines crossed, we'd get ourselves one solution. Our other possibility was, well, the two lines could be parallel. Okay, in which case, no solutions. Last possibility was that the two equations we were given were actually the same line, and they lied right on top of each other. And that, we said, was infinite solutions. Okay. We only had three possible outcomes because with the two lines, there's only three outcomes that could end up happening. Well, when we're dealing in three variables, what that kind of equation would graph isn't a line, but what's called a plane. It's kind of like a whole piece of paper. So you actually end up getting four possible outcomes. Those outcomes are this first possibility. Okay, if you think of taking three different pieces of paper, they could all technically intersect each other. All three touch at that same single point. They could all touch each other at a line. They could all be the same piece of paper on the same plane, and so they had all points in common. And then the last possibility is that none of the three pieces of paper ever even touch each other. None of the three planes touch. And there's actually four different ways, here, 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 and here, that could be the case. So it's kind of difficult to think of that visually or graphically when you're dealing with planes. So when you're dealing with 3 variables, you don't really need to know that for this class. I just kind of want to give a little bit of an idea of what we're dealing with if you were to look at it visually, graphically. But really what we need to focus on is the algebraic method in order to find out what outcome we have given our system. Most of them are going to be intersecting at a specific point, and we're going to find that order triple. But we do get some of these other cases where they're the same equations, or they are or there are no points in common. So let's start with that. Let me slide this up here. And using algebra, we're going to look at how do we solve a system of equations in 3 variables. So we're going to use algebra, and the method we're going to use is similar to when we had 2 equations. The last method we learned was elimination. We're going to use elimination again now. So what we do is, since we have 3 equations, we can only use elimination method on 2 of the equations at a time. So first thing I like to do when I have a system, I come and I label my 3 equations. We have equation 1, equation 2, and equation 3. Okay? So what we want to look for in these 3 equations is, first of all, could we add or subtract either of, taking 2 of the equations at a time, is there any that we could add or subtract as they are right now that would cancel out either our x variable, our y variable, or our z variable? Okay, so you want to look at, like, do any of your coefficients match each other, or are they opposites? But 4, 1, and 2, none of those coefficients match for the x's. 8, 7, and 3, none of those match. 1, -3, and 2, none of those match, nor are they opposites. Okay, so even if it was like a -3 and a +3, that would work, but we don't even have that in any of these 3 cases for x, y, or z. So the next best thing to do is to look at, take any of the equations where you have a coefficient of 1. And so looking at this, equation 2 has the x variable has no number out front. That has a coefficient of 1. We could make that x term have whatever number out front we want. We can multiply this entire equation by something. So we can make this match up with equation 3, or we can make it match up with equation 1 by multiplying something by this entire equation, since it doesn't have a coefficient. So that's where we want to start. So we'll call this step 1. And for starters, let's try to make it match up with the 2x of equation 3. So I want to multiply everything in equation 2 by 2 to make this term become a 2x to match the 2x of equation 3. So over here I'm going to write, we're going to take equation 2 and multiply everything in equation 2 by 2. So 2 times the x is going to give us 2x. 2 times the 7y is going to give us 14y. 2 times the -3z is going to give us -6z. And 2 times -14 is going to give us -28. Okay. So we multiplied there, and then we just want to take equation 3 as it is, because the 2x of equation 3 will now match up with a 2x here. So equation 3, as it is, was 2x minus a 3y plus 2z equals 3. Okay. Now we can do the elimination, use elimination, okay, because they are the exact same value out front, 2x and 2x. In order to cancel the x terms, we would need to subtract these 2 equations. Okay. So subtracting here, we will give ourselves 2x minus 2x. Those will cancel each other out. And here's where we have to be careful. We have a 14 minus a -3, which is technically adding. That gives us a 17y. A -6 minus 2 gives us -8z. Okay, -6 minus 2 gives you -8. And a -28 minus 3 gives you a -31. So what we just did is we eliminated the x variable, and we got ourselves a new equation that's only in 2 variables rather than in 3. So we can call this new equation that we just created, let's call this equation 4. We already had 3 equations. This is now equation 4. We're going to have to use this, but we'll come back to it. Okay? So, that's our first step. I guess if we want to kind of describe it, cancel one variable. Okay? We had to use some method. In this case, we had to multiply by something in order to cancel. Not always going to be the case, but either way, step 1, you have to cancel something. Step 2. Okay? We need to eliminate whatever variable we eliminated in step 1, the x variable. We need to eliminate that again. But now we need to use the equation that we didn't use in the first step. In step 1, we used equation 2 and equation 3. So somehow we have to involve equation 1 in this next step. So we need to eliminate x again. But this time using equation 1. Okay. So if we go ahead and take equation 1 as it is, with it has a 4x out front, we can use equation 2 again. That's fine. And because equation 2 has, the x value that with no coefficient, we can make that become a 4x by multiplying that whole equation by 4. So that's probably the easiest way to go about this step here. Okay, so we have equation 1. We can keep it as is, 4x plus 8y plus z equals 2. We want to multiply equation 2 now by 4 to get a 4x term out front. So 4 times equation 2 is going to give us 4 times x is 4x. 4 times 7y gives us a 28y. 4 times negative 3z gives us a negative 12z. 4 times negative 14 gives us negative 56. Okay. So now, because again we have the same exact x term, 4x and 4x, in order to cancel that out, we would have to subtract these two equations. That will eliminate the 4x's. If we were to add the two equations, that would give us 8x. That doesn't help us any. We're eliminating our x terms. Okay? And then in each other column, we have to subtract correctly. 8y minus 28y is going to give us a negative 20y. 1z minus a negative 12z. I've got to be careful here. When we're subtracting a negative, we're actually adding 12. So 1 plus the 12 actually gives us 13z. And then 2 minus a negative 56, again, is going to be adding. So it's going to give us a positive 58. Okay. We've now made a fifth equation, so I'm going to label it that. Equation 5. So what we now have are two new equations that are in two variables, just like we were dealing with in 4.1. So we can take equation 4 and equation 5 and do just the regular elimination we learned in 4.1 on those two. So that will be our third step. Regular elimination. So let's take equation 4, which which was 17y minus 8z equals negative 31. We also have to involve equation 5 now, which was negative 20y plus 13z equals 58. Okay. So, looking at our y's and looking at our z's, we want to determine which one would be easier to cancel. Unfortunately, 17 is a prime number, which means there's not going to be really any easy way to turn it into something that we can turn 20 into. Same thing with 8 and 13 on the z's. So, if that's the case, we could always make two numbers, two coefficients match each other by multiplying the 17 by a 20 and multiplying a 20 by a 17. Or we could multiply 8 by this top equation by a 13 and multiply 13 by an 8, and that's going to make those two numbers match. I guess let's just cancel the y's. So we're going to need to do that, we're going to need to multiply 20 times equation 4. Okay, so 20 times a 17 is going to give us 340y. 20 times a negative 8 is going to give us minus 160z. 20 times the negative 31 is going to give us negative 620. Okay. Then we need to multiply 17 times the bottom equation, equation 5. So 17 times negative 20 is going to give us a negative 340y. So those are going to match up and cancel when we do elimination. 17 times 13 will give us plus 221z equals 17 times 58 will give us 986. So unfortunately in this one we're dealing with some large numbers. That's why you have a calculator though. Now in this one, in this elimination, the y's we're trying to cancel, they're opposite signs. So we don't subtract when they're opposite signs, we add to cancel. So we have opposite y terms. So here we want to add. So we're going to add these two equations together. And we can move that over to the next page of the notes. Keep in mind the y terms will cancel each other out. We're going to add the z's and add the constants on the other side. So continuing the problem, when we do that, we end up getting 61z and 366. Okay. So now we have a basic equation in one single variable. We can finally solve this and determine what our z coordinate is going to be. So divide by 61 on both sides. And we end up getting that z equals 6. Alright, well, because we're looking for an ordered triple, that is only 1/3 of the process. We now need to find out what is our y value and what is our x value. So what we do is we can take 6 and plug it back into one of the two new equations we created. Okay? So if you look at either of those two, equations 4 or equations 5, because those deal with a z and they also deal with a y. Choosing whichever one you'd like. Let's see here. We could plug that z value in here, or we could plug that z value in here and find out what the y value is. Doesn't really matter, they both look about the same. I wouldn't say either one would be any easier than the other. So let's just use equation 4. Okay. So we're going to plug it into equation 4. So equation 4, we had 17y minus 8 times your z. But instead of z, we're going to plug in the 6. And that's going to equal negative 31. So go ahead and multiply the 8 times 6. That'll give us a negative 48. And I'll solve this equation for y, like we would solve any equation for a variable. Add 48 to both sides, and divide by 17. So, adding 48 to both sides here and here, we get 17y, 48's cancel, equals, what does this give us, 17 I have on my paper. And dividing on both sides by 17, we end up getting y equals 1. Alright, we're now 2/3 of the way done with the problem. We now need to just find our x coordinate so we can have that ordered triple, an x, a y, and a z. So in order to find the x coordinate, now that we know y and z, we have to go back to one of the original equations that involved x, either equation 1, 2, or 3. And because equation 2 doesn't have a coefficient on the x, that'd probably end up being the easiest one to find out what x is. So let's use equation 2, that x plus 7y minus 3z equals negative 14. Alright. So take that over here, and now let's use equation 2. So equation 2 was x plus 7y, so we're going to plug in 1 for y, minus 3z, so again we're going to plug in 6 for z, and that's going to equal negative 14. So now we have to multiply here and here, see what we get. We end up having x plus 7 times 1 is 7, minus 3 times 6 is 18, equals negative 14. 7 minus 18 gives us minus 11. So x, negative 11, equals negative 14. Adding 11 to both sides. We get that x is going to equal negative 3. So we now have all 3 parts of our solution. So we could come over here and write that our solution is the ordered triple. X coordinate always comes first, negative 3, then y coordinate 1, then our z coordinate 6. So we put it in parentheses just like any ordered pair. And that is elimination when we have 3 variables. I will cut this video and continue with the notes in the next one.